All right, this is Mr. Jern, and I'm going to go through some of these kinematics equations with you. I'm going to work through this practice. You'll notice at the top of your page that you have the kinematics equations. The first three are directly from the equation sheet. The last one is just sort of a bonus that we may or may not use. It's just kind of there to be potentially helpful. We're going to use the guess method because that's a very good strategy for deciding how to solve these equations, and just the process that's going to really, just help you not guess is really what it comes down to. So it's a good strategy. I want you to use this for as long as you possibly can. So we have question number one. A car starts from rest at a stoplight. The car accelerates at 2 meters per second squared for 6 seconds. What is the car's final speed? So a couple things we can do here. A couple things to note from the questions, and this is going to start to come a little bit more naturally as you do more of these, is you want to start noticing things when it starts from rest. Okay, that means that your initial velocity in the x direction is 0. Okay, I mentioned in the x direction because on the equation sheet it does have the x's next to the noughts. On this little preliminary set of questions, it doesn't have that. If the car accelerates, okay, so that's a key word right there, but also this 2 meters per second squared. When you see meters per second squared, or anywhere there where there's a distance and then a time and a time, that's going to be our acceleration. And since the car is a car, it goes along the ground, we're going to assume that it is going in the x direction. So it's going to be our ax, our acceleration in the x direction. 6 seconds will, of course, be our time. There is no direction for that. That's a scalar. And this question wants to know the car's final speed, which is just going to be velocity in the x direction. We could add that in there. Okay. That's something that you can do, especially when you're first starting these types of equations. Just go through the question and pick out all these things. You basically have completed the givens and the unknown. Okay, the givens, typically I do combine these steps, and I think after this one I will, but our givens are just kind of what we just went through. Vx, v naught x, the initial velocity, that's what that 0 stands for, that naught. We know that the acceleration in the x direction is 2 meters per second squared. We know that the time is 6 seconds, and that's basically it. Our unknown is the final speed, or the velocity in the x direction. So I'm going to put that right there. Again, normally I would just kind of put that in with the others, but for now it's fine. Okay, the equation. Now this is where listing the givens and the unknown will really, really help you. We've got 3 equations to choose from now. There'll be more later, right? So we now have v naught x. We have an initial velocity, so that could be this one. We have acceleration. Okay, we're winning. And we have the time. All right, so far so good. And we're trying to find v. It seems like this is the best equation to use, this very first one. And we don't even have to rearrange anything. It's just going to be Vx is equal to V naught x plus acceleration in the x direction times time. Hey, easy, right? Well, not easy. I won't say it's easy, but I should say it's very straightforward at this point because we didn't have to do anything. The physics is basically over with. In fact, a lot of times on AP questions, on AP test and test questions, you don't even have to plug in any numbers. In fact, they won't even give you numbers. But that's for another day. For now, we'll do with some numbers, and we'll actually do the substitution and the solving. So my velocity, and I'm going to probably stop using x, right? Well, it's too late. I already did it. They're all x's, so we don't need to differentiate. So this is going to be 0 plus the acceleration is 2 meters per second squared, and do not forget the units. Okay, just get in the habit of putting units in at all times. So what that's going to do then, our final velocity, so I've substituted, I'm going to solve, I'm just going to do v now. 2 times 6 is 12, and what happens with the units is we have one of these seconds is going to cancel out with one of these other seconds. And so we end up with meters per second. And always put a box around your final answer, because that's going to just make it pop. That is your final answer. And well, you want to make sure that you're not being confusing to anybody. All right, let me just scooch that back up so we have the equation still. Okay, question 2. Ida starts a race from rest. There's one of those, and speeds up to 9 meters per second. There's only one, there's no square here, so we'll get that in a second. And then 4 seconds, 4.0 seconds. Calculate Ida's acceleration. Okay, so she starts from rest. So once again, you know what, I'm just going to assume that we got all x's. And I'm not, okay, maybe we shouldn't make assumptions like that. So our initial velocity in the x direction is 0. She speeds up to 9.0 meters per second. So that's going to be our final speed in the x direction. And a clue for that is we just have a distance over a time, as opposed to up here when we had acceleration, it was a distance over a time squared, or a distance over a time over a time. So again, this is going to be our time, and calculate Ida's acceleration. So we need our acceleration in the x direction. Okay, so I'm going to list my givens and my unknown. My v naught x is equal to 0. And you may have noticed I put it in a different order. It honestly doesn't really matter. It's 2 adjectives is really what it is, and you can say them in any order. So this is the velocity in the x direction initial. Okay, there's not really a big thing. I mix those up all the time. Speeds up to, so my vx is equal to 9.0 meters per second. Let's make that decimal more clear. And our time is 4.0 seconds. We want the acceleration of Ida in the x direction. That is our unknown. So you can see how I combine the givens and the unknown. I do that a lot. I like how they're all right there for me. So now in this case, let's see, it looks like we have the same variables as before. We have v naught x, okay, there's that one. We have vx, the velocity in the x direction. We've got our time, and we got acceleration. So again, we're going to use the same equation as before. So vx is equal to v naught x plus ax, acceleration in the x direction, and time. One thing that you might notice I'm doing off and on is saying the full variable. Instead of just saying v and a and all that, it is really helpful to say the whole thing to yourself out loud, or at least in your head when you're doing this. So it just helps you remember all the variables, because there's going to be a lot of them. So we need to solve for acceleration in the x direction. Okay, so this one we do have to rearrange. That is not a problem. That's algebra. So I need to get this a by itself. So I'm going to subtract v naught x from both sides, because whatever you do to one side, you had to do to the other side. So that will cancel out that from over here. That leaves us with vx minus v naught x is equal to axt, acceleration in the x direction times time. I broke my own rule just then, but you can see how it would happen. We still need to get acceleration by itself, so I'm going to divide this by time, which will cancel that out. And that means I need to take over here, and I need to divide that by time as well. I don't like how that is not very clear, so I'm going to rewrite all of that as acceleration in the x direction is equal to vx, velocity in the x direction, minus the initial velocity in the x direction, divided by time. Okay, see how that's so much more clear than that smushed up mess down there? You want to be clear, not just for other people, but for yourself. Okay, this is really going to be helpful if you can be clear to yourself. That's essentially it. That's where a lot of questions will end in AP Physics, but for completion's sake, let's substitute and solve. So Vx, velocity in the x direction is, I could look up here or over here, 9.0 meters per second minus 0 divided by the time, which is 4.0 seconds. And so Ida's acceleration in the x direction is going to be 9 divided by 4. And since I don't have the answers in front of me right now, 9 divided by 4, 2.25. Hopefully that's the correct answer according to the key. All right, so we only have we're going to call it 2.25. We're going to call that 2.3. Now, it almost looks like the seconds might cancel out here, but you got to understand the seconds over right here is already it's already in the denominator. It's already under. So what we end up with is meters per second, also known as meters per second squared. So it could be that or meters per second squared. It's the same exact thing. And I'm going to put this in a box. It just means that she is speeding up. Her velocity is changing 2.3 meters per second every second. Okay, so it's a little bit more concise to say meters per second squared, but I kind of like meters per second, especially at the beginning, because it really does show a little bit more that it's a change of velocity over time. All right, we'll keep going. Superman is faster than a speeding bullet. That tells us nothing. If Superman flies at a constant speed, ooh, that tells us something. That underline that. It seems like it might be interesting. Of 350 meters per second. Okay, we'll come back to that. How far will he go in 45 seconds? Okay, let's do the easy ones first. 45 seconds is time. How far does he go? Okay, that's a little bit, how far does he go is sort of a, well, that involves X. I'll put it that way. All right, we've got some examples up here of X, so we'll get there. A constant speed, what that means is that I kind of wish I have a different color. Let's pull up a different color for this part. Or what I really should do is give myself more room. Whoa, look at that. All right, we're not going to use that very much. What this means is that my initial speed is equal to my final speed. Let's get away from that. Okay, that's what constant speed means. It means the speed doesn't change. So when I go to list my variables, in fact, let's give myself a little bit more room here. There we go. A little bit more room to breathe. All right, there. Now we can, now I can spread out a little bit. So what it means is that the initial speed is 350 meters per second. And it also means that the final speed is 350 meters per second. I kind of stopped talking about the X's because it doesn't matter. They're all going to be X's. They're all in the same direction. So that's why up here in the cheating area with the equations, they're not mentioned. Didn't change. How far will he go? Okay. One thing that might help is drawing a little bit of a picture here. We have Superman, a dot, because everything in physics is a dot. He starts at a certain position called position naught, or the starting position, x naught. He flies a little bit for 45 seconds, and he ends up over here. Okay. Since it's not specified, it's generally safe to say that x naught is equal to 0. Okay, and then x is going to be our question mark. How far did he fly? Sometimes you may come across a question where it does specify that he starts at a certain position. In that case, you'll just have to do a little subtraction and take it into account. So I know that I'm going to list this, the starting position, we're going to call it 0 because nobody said we can't. And so my final position is going to be the question mark. And here I am mixing up my givens with my unknowns. What else we got? How far away? 45 seconds, the time. Time is equal to 45 seconds. Okay, I think I've got everything. Let's find out. I'm going to my equations up here. This first equation, okay, we got velocity, final velocity, okay, initial velocity 350, okay, acceleration is not mentioned, okay, but we can kind of conclude, since it's a constant speed, that acceleration is 0. So I guess I'll just squeeze that in there. Maybe that will matter, because 0. The problem with that is if we use our brain a little bit, we're going to realize that acceleration time is 0. This is going to be 0. And then we're going to basically say 350 is equal to 350. That's not exactly what the question's asking. Plus, look I should have even realized this right away. There's no x in this equation. We can't use this at all. So we move on. This one does have x. What do you know? It's also got a. We'll deal with that. It's got initial velocity, 350. The time, we know that, 1/2. A is going to be 0. And this one might work, actually, as it's stated. You will notice that on the equation sheet, it is a little bit different. It does take into account the initial position and all that. But again, we're easing into it a little bit. So I'm going to try this equation. It might not work. It might work. What does this one do? Okay, okay, well, we're going to end up with the same thing as the first part, because this is going to be 0. And then, yeah, okay, that 350 squared will be equal to 350 squared. We're going to move on. We're going to choose this equation. So x is equal to v0 times time plus 1/2 acceleration times time squared. Okay, we've already said the acceleration times time squared, acceleration is 0. So what I'm going to do is this little fancy maneuver where we know that it's 0 and everything times 0 is 0. So this whole thing over here at the end is 0. Now I want to know, okay, well, hey, it looks like we're already set up to find x, which is what we're trying to find. Great. So I'm going to substitute this. By the way, a lot of times, like I said, in AP Physics, that would be practically the end of the question. You wouldn't even have to go any further than this. But this isn't, we're not quite there yet. All right, so 350 meters per second. Because we're multiplying like this, I'm going to put things in parentheses. It just helps keep things organized, and especially with the units in there, it really does help. Times 45 seconds. All right, right away I could tell seconds is going to cancel out, which is great because that's going to leave meters, which is what we want. We want meters. All right, let's solve this thing. X is equal to 350 times 45. So 350 times 45. That's a big number, but it is Superman. So I got 15,750 meters. All right, seems to be good. One thing you may have noticed is that this extra special bonus question or equation over here would have actually done the same thing. You can use it. I think in future I'm going to take this out because this is not listed on the AP physics equation sheet. So that's why I didn't even talk about it. Okay, question 4. All right, I'm going to need a little bit more room, but I'm also going to try to keep those equations down there. Doot, doot. Oh, they're just going to stay down there no matter what. Doot, doot. And move that guy down there. Boop. Okay, so we should, I don't like it highlighted though. All right, nothing like adjusting my screen while I'm talking and recording, right? Number 4, how long does it take for a toy car starting from rest to travel a distance of 5 meters if it accelerates that much? How long does it take? That's code word for time. It's starting from rest. That's another thing to keep in mind, or at least keep an eye out for. And it has to travel a distance of 5 meters. And it tells you the acceleration. All right. This is why I really like to I just combine the givens and the unknowns, because I just kind of read it and I put it in this order. So the time is what we're looking for. From rest, so V0 is equal to 0. Travel a distance of 5 meters. So again, going back to our Superman drawing from earlier, I'm just going to assume it starts at 0. X0 is 0. And so our final position is 5 meters, and then it accelerates at that much, 0.8 meters per second squared. Okay, what equation do we use? Well, we had to have an x, so this first one is out. Looks like we have to have they all have a in it, so that's good. Well, let's just try this one. So x, yes, v0, we know it's from rest, that's going to be 0. A we've got, and time is what we're trying to find. All right, looks like we're going to have to do a square root, but oh well. All right, so I'm going to start with this equation. X equals V0 times time plus 1/2 a time squared. All right, so I need to rearrange this though. So let's do this. Oh, wait, first of all, V0 is 0. Look at that, I can just get rid of that. That makes things so much easier. All right, so Now I need to get I need to get t by itself. So I'm going to divide by 1/2. I know dividing by half is kind of like, but it is what it is. It's going to cancel that out. So that means this side I got to divide by 1/2 a. So that means I've got 2x divided by a is equal to 2 times the position divided by acceleration is equal to the time squared. So the time squared, we have to square root that. So the time will be equal to 2 times the position divided by the acceleration, and we take the square root of that. All right, let's plug these numbers in. Time is equal to, one nice thing about being able to plug the numbers in is if you get a reasonable answer, it does seem like it's kind of a check to make sure you did this part correctly. So 2 times the position, the distance it travels, 5 meters divided by the acceleration, 0.8 meters per second squared. So if I put that into my calculator, which likes to move around on me a lot, so 10 divided by 0.8, and then I take the square root of that answer. If you'd like, I could show you how to take square roots of your previous answers in your calculator. It is super handy. Can you see it? Let's see. See how it just says square root of the answer? If I could focus. Okay, square root of the answer, really handy. Also, please don't write all those numbers in there. It's we'll go with 3.5. Okay, what happens here? Meters and seconds, they cancel out. So I'm sorry, meters and meters cancel out. One on top, one on bottom. Seconds squared is on the bottom of the bottom. It's the numerator or the denominator of the denominator. So that comes to the top. And since it's square rooted, our final answer is in seconds. That is a check. So like you should get the units. Okay, I'm gonna actually, units are a check to see if you're doing it correctly. It's such a great thing. If you get the correct units, there is a very good shot that you did it right. A very good chance you did it right. Okay, ball rolls down a hill. Acceleration. Oop. If it starts from rest, that's important. How fast is the ball moving? Now let's continue after traveling. So that's going to be our final velocity, this distance. So the acceleration is 3.0 meters per second squared. It starts from rest, so our initial velocity is 0. How fast is the ball moving? So our final velocity will be our question mark. And traveling, okay, again, look at our Superman picture from earlier. Starting at position 0, which is the starting position 0, it has traveled 6.0 meters. Not meters per second. What am I thinking? Let's clear that up a bit. Just meters. Okay, be careful with that kind of stuff. You get distracted, like for example, you're talking while recording a screencast or being on your phone, or just focus when you're doing this stuff. Things go faster and you get things done you're more likely to get it correct. Okay, which equation should we use? We can't use this one because again, x is present. So can we use this one? Should we use this one, I guess is the question. Yes, we got that. We got initial velocity is 0, so that goes away. 1/2 a, good, we got that. And we've got, we don't have time. We can't use this equation. This last one better be it. Velocity, yes, we're trying to find that. Initial velocity is 0, we're good. And 2ax, we got both of those. All right, we're using this guy. So v squared is equal to initial velocity squared plus 2 times acceleration times the position, change in position. You'll notice on your equation sheet, this does have the change in position. It doesn't just have x, it has, I believe it has x minus x naught. So minor change. Okay, so it starts from rest. We know that initial velocity is 0. I don't need to worry about that. How fast is the ball moving? Oh, hey, look at that. We're just trying to solve for v. This is going to be, look at that. Okay, it's squared. So what do we got to do? We have to square root the other side. We got to square root both sides. So there we go. All right, so again, A lot of times you wouldn't have to solve this part, but it's really handy to do so. So 2 times the acceleration, 3.0 meters per second squared, times the position change, meters. This is why I don't draw the square root until the end. Now I gotta do that. All right. Don't forget to take the square root at the end. This is a very common, in fact, I'm gonna use my fat red pen to point that out. Don't forget to do that. All right, so the square root part. So 2 times 3, I guess I could have done that part, times 6, it's 36. Square root of 36, surprisingly, 6. So the velocity is 6. Now, do I get the correct units? That's the key. So meters times meters per second squared times meters, I'm going to end up with, on the inside here, I'm going to get meters squared per second squared, which is great because when I take the square root of that, I get meters per second, which is the unit of velocity. Okay, one more. Where was I? Oh yeah, square root. I'm just going to put that there for posterity. Okay, a car initially moving at 10 meters per second. So we're going to have a v naught of not 0 and accelerates this much. What is the speed of the car after it travels this distance? All right. So our v naught is finally not 0 meters per second. The acceleration is 0.5 meters per second squared. We want to know the speed at the end, and we know that it travels 100 meters. All right, we got our givens and our unknown. That's going to inform which equation we use. We have an x, so we cannot use this one. Ooh, it's the last question, so I'm actually going to go, don't use that anymore. Now, the question is, in this one, you know what? I just don't like you. You kind of like, I don't know, it annoys me. And so we've got x, okay. V naught will be 10 time, oh, we don't have time. So we don't have time. We don't have the time, so we don't need that equation. It's got to be this one, v naught, okay. 2, okay, yeah. A, yep, and x, okay, good. So we're going to use this one again. V squared is equal to v naught squared plus 2 times the acceleration times the position. Nothing is 0, so I don't get to do the little fancy zeroing out thing. So I just had to take the velocity is going to be, I'm going to put the square root in last this time, although that really plays more of a role when I put the numbers in. Plus 2 times the acceleration times x, and I do have to take the square root of all of that. Now, don't let this deceive you. We are adding these two together. You cannot just change this to v naught. This is all because of the plus. You have to take care of that before you do any square rooting. Okay, so that does not become unsquared. All right, let's plug in our numbers. V is equal to, now this is where I'm going to put the square root in last. V naught squared, so 10 meters per second. I almost put squared there. Okay, ooh, everything got erased. Per second. And I'm going to square that plus 2 times 0.5 meters per second squared. Now I can do that. Times the 100. No, yeah, times meters. Now I have to take the square root of all of that, and we'll see what happens. All right, well, first of all, I hope these units are correct. So I'm just going to do a little preliminary, multiplication in here just to make sure. So this will become 100 meters squared per second squared plus, I'm going to calculate this because you can't, just because you can do it in your head doesn't mean you should, right? Do you trust yourself? You should a lot of times, but when it comes down to it, yeah, okay. So this is kind of what I was thinking. It is going to be 100. So it's 100. And what happens, this is similar to above where the units didn't cancel out. The meters didn't cancel out. They actually multiply together. And so we do have like units, which is a good sign. We can actually add these together. So I'm going to now solve this, and I need to take the square root of 200. Who came up with this question? Why didn't I just make it square root of 100? Oh well. So the square root of 200 is 14.14, although I do kind of like that. 14, unfortunately I got to round it to, yeah, well, I probably should have rounded it to 14, but I'm going to leave it there because I don't like it without it. And look what happens again. The meters per seconds become unsquared, and we get meters per second. The meters squared per second squared become unsquared, and we get meters per second. Okay, so there we go. Hopefully that helps you. If you have any questions, please let me know in class. Thank you. If you see any problems or mistakes I made, also let me know. I'll give you bonus points. Bye.